If you could see the ultraviolet.
Well, I don't know. Quick. So everybody, close everything up. Have a look up here. We won't have to do this all period. I want to just help you understand this relationship because this is an important relationship. So if we want to talk about the rate of change of volume with respect to radius, okay? Well, let's take a sphere for example, right? So I guess that's implied we're talking about a radius. So what is, if we want to look at the rate of change of volume with respect to radius, without even putting anything up there, just kind of not even thinking about this, what does that predict that we're going to be doing in terms of calculus? A derivative is a rate, right? So what derivative does this correspond to? The derivative, the rate of change of volume with respect to radius. Okay, but what, so if we come up with the volume formula for a sphere, I would write it like this. V of R equals what? What's volume for a sphere?
4/3 pi r cubed.
Okay, why would I write it as V of R?
Volume of this radius.
Say it again. Volume of this radius equals
With respect to radius.
Okay, so R would be the independent variable, right? The input variable, V is the output that we're calculating. So if I were going to graph this, for example, I wonder where I could find a graph of that. That should be nice if I had one of those somewhere. Where could that be? I don't know, but where could that possibly be, do you think? Let me save this real quick.
I shook.
Oh, the Mandelbrot set?
No, that's something different I was working on.
Oh, disappointing.
You woke up. I woke up. I was like, wow. What is this book?
Okay, so here it is. There's our graph, right? If I graph volume as a function of R, that's it, right? So for example, if I put in a radius of 1.8, that's just going to give me back, and I bet I can even, a little tricky here, I bet I could even,
Which is better, GeoGebra or
GeoGebra for this kind of stuff is a little bit better, I think. Well, I don't know. Anyway, so that's my volume function, right? So if I graph that function, you know, the R is going to be the independent variable, so we graph R on the horizontal axis and V on the vertical axis, and that's what we get, right? So for any input of R, I get back a value of V. If I input 1.8 for R, I get back a volume of 24.4, right? Whatever units we're talking about, you know, cubic centimeters, cubic meters, whatever we're measuring R in. Okay, so back to my question. What are we talking about? A rate of change of volume with respect to radius. What is that referencing in terms of calculus? Okay. Which derivative? Am I taking derivative of?
the derivative of VR.
Okay, but what do I write up here?
V prime of R.
Okay, so I could write V prime of R. So all this stuff up here, the rate of change of volume with respect to radius, that's the same thing as V prime of R. I could also write it as dV dr. And here's why. Because we're talking about the rate of change of volume. That's that part. With respect to R is that part or that part, right? It tells me what is my derivative, how am I building this derivative, right? I'm differentiating V of R, or I'm taking dV dr, the rate of change of volume with respect to radius. Okay, that's important. Because I could, now this is gonna sound weird to you now, but I could do something completely different. I could do something like dv dt, and that's a totally different animal, right? That doesn't really mean a lot to us right now because there's no t up here, there's no dependence on t. But that's what that derivative would mean. We're talking about the derivative of v with respect to r, right? So how would I represent that on my graph? Okay, like let's say, what is dv dr? First of all, let's find that. So v prime of r, this is a pretty easy one, right? This is just a power function. I'm using my power rule. I've got some constant out front times r cubed. Maisie, what's the derivative of r cubed? 3r squared, right? I'm going to subtract 1 from that, pull it out front. So that would be 4/3 times 3 is 4 times pi r squared, okay? Okay, that tells us tangent line, right? So let's pick maybe a little better value of our input. How about if we pick our input to be like 2? Okay. Where's my tangent line? Right there. There we go. Okay, where's my slope? Right there. So if I were to take the point when r equals 2, volume's roughly 33.5, rounded. Okay? If I draw a tangent line in there, the slope of that tangent line is 50.3. How am I going to get that? How am I going to get that 50.3? Yeah. The value, the point on the graph we get from v of 2, which is 4/3 times pi times 2 cubed, and that's roughly equal to, what was the value? I can't remember. 50 something. It was 50.3. No, I can't. I've tried. 50.3. If I want to calculate what the value of the derivative is, well, that's just 4 times pi times 2 squared, which is roughly equal to, oh, I get that backwards. That's the one that's 50.3. It's the value of the function that's 33.5. So let's change that. What was this other one again? 23.5? 33.5, I can't remember. Whatever it was. 33.5, okay. Right? That makes sense? Okay? So what does that mean? What does that mean? If we talk about the rate of change of volume, this is an instantaneous rate of change because it is the slope of a tangent line. That's something that people sometimes have a hard time wrapping their brain around first, right? So this gives us instantaneous rate of change. Okay, what is that? Can you describe that? What is an instantaneous rate of change of the function? So if I say that the value of the derivative is 50.3, in other words, the rate of change of volume when r equals 2 is about 50.3, what does that mean? What does that mean? Well, what if I take a time interval that's surrounding that? So let's take some points that are going to be plus or minus 1 from that point. Okay, so I got to maybe shrink this down just a little bit. So 1 is going to start at 1 and end at 3. Right, we'll take that little interval, and on that interval, let's calculate the slope of the secant line. I get 54.5. right? So if I look at the average rate of change, if I look at the average rate of change of volume as the radius goes from 1 to 3, that's what I get, right? If I'm blowing up a balloon and I increase the radius from 1 to 3 of the balloon, at what rate is the volume changing? On average, it's changing by 54.5 cubic meters, or cubic, whatever we're measuring, cubic meters per meter of increase in radius, right? Okay, does that exactly match what the tangent line is here, though? It doesn't, right? How come?
Because that's taking the average over the infinite number of points that exist between the two.
Right, I mean, so the average over that interval is pretty close, but notice that this curve it's not changing regularly, right? It's getting steeper at a rate that's not linear here, right? What's gonna happen though if I bring in those secant lines, if I get them closer and closer? So let's just shorten up that interval where we're calculating an average. As I make that interval smaller and smaller, look what's happening to the slope.
Which is closer and closer to our value.
It's getting closer and closer to the value. Does it ever actually get there? Well, no, to 1 decimal place it is, right? So then what does that instantaneous rate of change really mean? It means, like, if I were to, I mean, it's hard to articulate, but if I were to try to get that one instant in time, so the radius is changing the volume in a way that's not linear, right? The further we move along to the right on this axis, on the x-axis or the r-axis, the steeper this graph gets, right? So the volume is changing at a rate, if I go out here to r equals 2, it's changing at a rate that's different than it was at r equals 1, right? Think about when you blow up a balloon. When you blow up a balloon, initially, as you're blowing it up, it's pretty satisfying. The first few breaths, that thing gets pretty big, right? But what happens after a while?
The rate increases.
And you don't start to get as much bang for your buck after a while, right? When every breath you take after a while, you hardly even see any increase in the radius of this thing, right? So as you're adding volume to this thing, it takes a lot of extra volume after a while just to move that radius along just a little bit, right? And depending on what size the balloon is, it determines how satisfying that is, right? I don't see much, you're not getting much, after a while you just quit, because you're not getting much volume for all that, or much radius change for all that volume you're adding, right?
Isn't that the essence of the square cube law?
Well, kind of, but yeah, kind of. That's what we're getting at, though, is that it's non-linear, right? So what is this telling us then? This is giving us a number, essentially, that's telling us how much bang for your buck are you getting when you're blowing up that balloon, right? The higher this slope gets, the worse off you are, right? Because that means the volume is taking a lot more volume. Each little increase in radius goes along with a much larger increase in volume, right? When you're blowing up the balloon, you're adding the volume to get the radius increase. And so to get right up here, like if I'm clear up here, to get that radius to go up a tiny bit, I got to make the volume go up a lot. Down here, to get that volume to go up, a lot, I don't have to add very much, right? One little puff. One little puff, that tiny little bit of change in volume moves the radius along quite a bit. You see that? Get the difference? So that's what this slope of a tangent line is really getting at, is at that one point on the volume radius graph on the curve, how are those rates of change related, right? As you increase the radius, how much is that actually increasing the volume, or vice versa, right? It's like if you're in your car and you're driving along with your speedometer. If you're accelerating from 0 to 60, right when you hit 30, how long are you actually going 30 miles an hour? I mean, for just an instant, right? There's not even an appreciable time because it's a continuous change in speed, right? So when you look at the velocity and it says 30, you look up and you look down and it's gone, it's changed, right? It's already gone. But what did that 30 mean? It means something to you, right? 30 miles per hour, you can equate that in your mind to how fast you're traveling at that moment along the ground. It's changing, every instant is changing, but that 30 still has some meaning, right? It's not an average. it's what's happening at that one instant, right? You get the idea? You see the difference? You know, if you're ever talking about, like, when you calculate in your, who's in physics right now? So when you guys talk about calculating a velocity or a speed, it's always an average, right? You're always saying displacement or distance divided by time, right? You're never actually talking about an instantaneous velocity in that class because you're not doing calculus. You can't do it. It doesn't make any sense, right? You got no way to come up with, you have no way to make that calculation. In order to make the calculation of what your instantaneous rate of change is, your instantaneous speed, or your instantaneous rate of change of volume, right? You gotta take a derivative. Everything else you would do, it might be a good approximation, like that secant line is, but to get the actual answer, you have to take a derivative. That's the meaning of a derivative.
Assuming the acceleration stays constant.
You don't even have to assume that. You don't have to make any of those assumptions. If you have a function and you differentiate it, the value of the derivative means the instantaneous rate of change. You don't have to, nothing has to be constant at all. We could pick the wackiest function in the world, but if I take a derivative and I evaluate it, that's giving me back the instantaneous rate of change, right? Okay? So let's look at a little example of like what's going to be on the homework. So what about something like this? So this is just some crazy function. The view v, or distance in miles, that one can see to the horizon from a height h in feet is given by this function. So here it is. So this is view as a function of height equals 1.38 times the square root of h, right? So find the rate of change of v with respect to h. What is that? Rate of change of v with respect to h. Rate of change means derivative, right? So right away, let's just dissect this statement. Rate of change is derivative of v with respect to h. So put all that together, and what are we saying? Well, that's just v prime of h, right? Or another way of saying that, if I want to use a different notation, dv dh. Either way, they mean exactly the same thing. So what is v prime of h?
1/2 times 1.38.
We'd have to write that as 1.38 times h to the 1/2. Okay, so Joe, tell me now, how am I going to take that derivative? What do I get?
6.
Joe? Yeah, okay, times the 1.38, so that works out to be 0.69.
And then it's going to be h to the negative halves. And then you could also just do, so then it would just be 0.69 over h to the thingy that is the square root.
There you go, very good, right? So there it is. There's our function, right, for v prime of h. So if we want to know how far can one see to the horizon from an airplane window at a height of 10,000 feet, so I want to know then, Liz, the blue or the black, which one am I going to use if I want to answer part B? How?
One of them's right.
You're right. One of them's right. So what does this one stand for again? What is that telling us? So is that standing, the view, right? That's giving us view as a function of height. This is giving us rate of change of view as a function of height. Good. So what are we asking for here? How far can one see to the horizon? That's the blue, yeah, right? Because that's the definition of what we call view. What's your view is how far can you see from a certain height, like in an airplane, right? So we're going to, for part B, we're just calculating v of 10,000 and getting some answer. Who cares, right? What about part C? Find the rate of change at h is equal to 10,000. So which Luke, which one am I using there?
Black.
Black, right? So part C. Part C is gonna be V prime of 10,000. Okay, let's actually evaluate that one. What do I get? So square root of 10,000 is 100, so I'm getting 0.0069, is that right?
Yeah.
Okay. And what are the units gonna be for that? What would the units have been for this guy? So that would have been, let's go ahead and do that one real quick. So I'm gonna get square root of 10,000, 100 times that, so I would have gotten 138. And those are measured in, I think, is it miles? Miles, right? So from 10,000 feet, if you're up at 10,000 feet on a mountain and you're overlooking the ocean, right, you ought to be able to see 138 miles out on the ocean if you're that high, okay? What's this going to be measured in? So I'm measuring V in miles, right? What am I measuring H in? Feet. In feet. So no, what's it going to be then, Kyla? If I'm measuring V in miles and H in feet, what's dV/dH can be measured in? Miles per foot, right? Anybody see that? Okay. So I'm going to get back here roughly 0.0069 miles per, whoops, that's not it. So somebody, what is that? What is that? What's that mean then? So if I plug in a 10,000 into V prime, that's the rate of change of view with respect to height, and I get back a number of 0.0069 miles per foot. What in the world does that mean?
Is it like how many miles you can see for how many people?
Well, at 10,000 feet, I can see about 138 miles out there. But if I'm increasing, if I'm still moving up, let's say that I'm walking up the mountain. For what? Per foot, okay? Now, you got to take that with a grain of salt, because if I actually step up, let's say from 10,000 to 10,001, is there a guarantee that I've moved up by exactly 0.0069? Now, the curve's changing maybe, right? So when I actually go up to, right, when I actually move up that extra foot, that may not be how much it's changed, but at that instant, if I were going to make a prediction, so if I were going to make a prediction, I would say at this rate, I'm going to be moving up by that many miles per foot, right? If everything stayed the same. Now it doesn't, because as I move higher, the view function is changing things, but that's telling me, giving me a numerical quantity for how fast is the extra horizon becoming available to me visually as I move up there, right? Now, if that number were lower, then that means that, like if I'm lower down to the ground, as I move up this thing, like if I plug in a different value, like let's just plug in 100 instead of 10,000 and make a comparison. V prime of 100 is roughly equal to 0.69 over 10, right? The square root of 100 is 10. So I'd get 0.069 miles per foot. So if I'm only 100 feet above sea level on a little bluff by the ocean, and there's that big mountain up there, in which case, as I'm walking up, let's say at 1 foot every second, in which case am I going to see the horizon unfolding before me faster? Yeah, there, right? And about 10 times faster, right? So as I'm closer to the ocean, as I walk up, I'm seeing that my horizon extend faster than I would if I were 10,000 feet up. Does that give you a sense of what that means then? We're putting a number on this to kind of describe how fast that's changing. Okay? If I'm walking across the front of the room, and I would notice As I walk across the front of the room, people in the front are moving by my field of vision faster than people in the back, right? They're both moving by my field of vision, but if I were to attach a number to this, like a rate of change of their position in my, according to me, that would be a higher rate than that is, right? That quantifies it for me. I can put a number to how fast are people moving across my field of vision, right? That's a rate. Okay, does that make sense? Okay. All right. Okay, so what about something like this? If an object is dropped from a 100-foot high building, oh, actually, I don't want to do that one. I meant to delete this. Let's get rid of that. We'll just take all this stuff. Okay, so let's look at this. Here's a position function of an object in free fall. V sub 0, we call that V naught, represents the initial velocity. S sub 0 or S naught represents the initial position. Well, we say S naught. I'm not talking about snot, it just blow my nose. But when you have a subscript of 0 in physics, we call that naught. Naught is
knob.
naught. No, naught means 0 in English. I think it's in England where they call it naught for some reason last time. Not exactly. They say it like that too. Okay. So we're going to try to do something with this. Here's our formula, right? Just in general, if we're measuring position in feet and time in seconds, this is the equation that we use to forecast, position of an object. If we drop a coin from the top of a 1,362-foot tall building, determine S of t and V of t for the function. Okay. So what's S of t going to be? So what's our formula to come? If I'm dropping it, what's the initial velocity? Okay. Everybody agree with that? If I start the videotape right as I'm releasing it, the initial velocity is 0, right? So we're going to get negative 16t squared plus 0t is just 0. What's my initial position, Emily? 136.
The height of the building.
There you go. 1,362 feet. So there's my position function. Okay, what is my velocity function? Well, remember, velocity is just the derivative of position with respect to time. Okay. So what's that going to give me, Kyla? Negative 32t, good. That's it, right? The other one's going to go to 0, okay? So there we go, determine S of t and V of t for the coin. So find the average velocity of the coin on the interval from 1 to 2. Well, that's easy to do, right? An average velocity is just going to be the average rate of change of position, okay? So average velocity, let's add, so a little more room here. So if we want to do an average velocity, in physics, we put a bar over the top for average. So average velocity, instead of being an instantaneous thing, it's just going to be the change in position over the change in time. That's just a difference quotient. So we're just going to get S of 2 minus S of 1 over 2 minus 1, right? That's all an average is. We're looking at the slope of a secant line. So we want to know what's the position at 2 minus the position at 1 over time 2 minus time 1. If I were to graph this thing, it would just look like if I'm graphing, and it's really good to think about this stuff in terms of graphs. If I'm graphing position on the vertical axis, time on the horizontal axis, it's just going to look like this, right? You see that? Just the downward slope parabola, with my initial point is gonna be at 0, 13, 62. And if I'm going between 1 and 2 seconds, let's just say it's between there and there, right? So I'm just finding a slope of that secant line, connecting those 2 points, right? And what's that give me? If I plug in 2, what do I get? So 4 times 16 is 64. So negative 64 plus that is 1298. Minus 60, so that's going to be 1346. Is that right? Over 1 is what? Negative 58? Good. I feel better about that. Negative 58 feet per second is my average rate of change. Okay. Find the instantaneous velocities when t is 1 and t is 2. Okay. Well, that's easy to do. We have a velocity function, right? That's what the instantaneous velocity is, what the derivative gives us, right? So v of 1 is negative 32. V of 2 is what? Negative 64, okay? So does that make sense? The average rate of change was somewhere in between these, okay? Why might that be the case? Liz, why would that potentially be the case here? Why would the average velocity over that interval from 1 to 2 seconds be in between the instantaneous velocity at 1 and at 2? What's this thing going to do? As I drop this object, what's it doing as it falls? It's accelerating. What's that mean in terms of velocity? Okay, increasing velocity, right? So after 1 second, it's got a certain velocity, negative 32. So the speed is 32 feet per second downward. That's the negative sign, right? After 2 seconds, it's picked up to 64 downward, right? So over the average, doesn't it make sense that it's going to be somewhere in between? Right, because part of the time it's going slow and part of the time it's going real fast, and so on average it's going to be in between. Make sense? Okay? Kind of, sort of, maybe? We getting this? Okay? Last question. How fast is the coin traveling when it hits the ground? This is the one I'm interested in. This is really cool. So think about this. How are we going to find? Good. Good. So we're going to set that equal to 0, right? We want to know when is the position equal to 0. Good. That means hitting the ground. Okay, so 4. 13, what the heck was it?
52.
52?
62, it's right.
Oh, there we go. Okay. Is it where? I don't see it. Oh, there it is, right there. You're right.
Okay, now that's on YouTube forever.
Okay, it is. So that's easy to solve. So that just gives us 16t squared equals 1362. Divide by 16. That's no big deal. What's that give us? 16 times 8 is going to be 128 with
85.125.
Okay, that's good. So 85.125, you say?
That's an 8.
That's an eighth. So that's going to give us
82 and an 8.
85. So 1's
Trying to square root that.
6,
Or what?
81 over 8. Is that right?
Sometimes.
Is that right?
Should be.
Is it?
681 over 8. Yep.
Oh, yeah, it is. Okay. Good. Okay, so t equals that. So t, or that's t squared equals that. So t equals, mathematically, plus or minus the square root. We'll just get that as a decimal. What is that, somebody?
82. 85.125.
85.125.
Yeah, I read 85.
I said 85.125
That's
3 minutes
T
ago.
Yeah.
Oh, that's that. No, but I want to know
Oh.
What's the square root of
I'm on it.
that? That'd be way too high anyway, yeah.
9.226.
226 to 3 places?
Yep.
Okay. So that's about how long it takes to get to the ground. Now, hold it, do I want the plus and the minus?
No.
I don't. I just want the plus. Does the minus have any meaning?
It means going down.
Okay, yeah, the math gods, the physics gods never give us anything that's not somehow important. It may not be what we want, but it does have some meaning, right? Here's what the meaning is.
We're time travelers.
No, here's the meaning. Here's the meaning. If I were to, let's look at this function. Let's look at this on Desmos, how about, real quick? This is pretty cool. Okay, so negative 16x squared plus 13, what was it?
1362.
I know, I'm just teasing. It's right in front of me. Okay. So if we look at this, and I zoom out,
Oh my.
right, there's,
That's a y-intercept of 1363.
I guess you're correct.
it does, it has a y-intercept of 1362, so let me fix this real quick. Let's go negative 100 to 1370, good enough. And this is going to go from negative 10 to 10. Okay? So there's what this thing looks like. Now, we really only were interested in the part that started at t equals 0, right? Because we're going forward in time for when we drop this thing, right? And so this is the path it takes, the velocity time graph, right, or the position time graph. So the tangent lines get steeper and steeper and steeper as it picks up speed. But what if I were to go back in time? Notice that if I were to go back in time, if I reverse time, it would have gotten to the ground in the same amount of time that it took when time went forward. Well, what would that mean physically? Okay, so instead of, we could change the parameters of this thing. This is, now hold on to this, this is pretty cool. So instead of just dropping this thing from rest and having it take 9 point blah, blah, blah seconds to get to the ground, I could have instead had somebody throw it up from the ground with a really high initial velocity. So it comes right up and it's right between my fingers, and then I never actually grab it and just let it fall down again. And maybe you wouldn't know the difference. Maybe the camera just started filming when it looked like I was dropping it. But the object actually rose up to here, and then they start the camera, and then it falls back down. I never actually touched it. In that case, how long would it have taken the object to rise up to be right between my fingers? Same amount of time. So that negative time really does actually have some meaning, right? And the physics gods don't understand things like hold on to something. They just know physics quantities. They know the initial conditions were velocity 0 at time 0, right? They don't understand, grab this thing. They just know that's where it was at that time. So from their perspective, it easily could have come up from the ground to get to that point. Right? Make sense? Okay. So then, if I want to know how fast it's going, we got our answer. So Maisie, you started this off, you finished this off here. You got this. So if I want to know how fast it's going, I calculated that it takes 9.226 roughly seconds to hit the ground. How would I know how fast it's going at that time?
Plug it back in.
To which one?
The red.
The red one, V of t. Very good. Right? All right. Woo! Okay.
We're done?
We're done.